The first talk, the title is on the screen, and the list of colleagues include a team from people who do ARPIS measurements in United Kingdom, Timur King and Jung, and Daniel Yevtushinsky in Lausanne, people who calculated band structures, who did measurements on cyclotron in Grenoble, who did measurements in X-ray circular magnetic dichroism in Spain, Dmitry Rodichev with his scanning tunneling microscope in France, and Vasily Stolyarov, Golovchansky also did scanning tunneling microscopy. Denis Velych, Eugene Chulkov calculated band structure and so on. The same theory team included Vladislav Borisov, Roger Valenti, Artur Ernst, Sergei Yeremeyev, and maybe I missed someone else, but please excuse, the list is quite long. All this more data can be found on already published papers, and the last one is in press. So I proceed with the results. The first, I have to explain the motivation, then I will go to crystal structure and surface morphology, the band structure, the electronic band structure, superconducting properties, and the magnetic properties. The material which is on the screen is quite attracting, and there were several talks already on this conference, and probably today more. It's attracting because it's material which is in stoichiometric composition is superconducting. It doesn't include any doping, and it comprises long-range magnetic ordering of local magnetic moments of europium with itinerant 3D electrons of iron. At the same time, it is well known, it is already established that pairing, superconducting pairing of 3D itinerant iron electrodes happens via magnetic fluctuation. So it is quite a complicated story. The magnetic ordering of the europium atoms, europium planes, appears to be not trivial. It's like a helix. And the planes are quite located quite away of each other. So it's the mechanism of establishing the long-range order is not quite clear. It's discussed, and I don't think that it's clear. Because the same iron orbitals participate in, actually they form a Cooper pairing. At the same time, they should transfer the long-range magnetic order between the europium layers. And finally, there is some special flavor of this story that the magnetic ordering happens inside the superconducting inside the superconducting phase below the temperature of superconductivity. So all these questions can be shortly summarized as follows. How does the europium helical order coexist with superconductivity in iron arsenide planes? First, I show here the crystal structure. This is the top view, and this is a side view. In a side view, you see that the primitive cell consists of two blocks. It's actually alternating europium 122 and rubidium 122 blocks, and they are put on top of each other. And since and therefore they must be intrinsically uh, uh, because of the different intrinsic primitive cell size, they should be intrinsically deformed, and this may be the reason of the superconductivity to happen with no doping. So the size of rubidium atoms and europium atoms is different, and it also must be understood how the cleavage happened, because all the measurements happened with the cleaved, vacuum cleaved and low temperature cleaved surface. So we first study how the native surface opens after cleavage. And what I want to add in the story, that the superconductivity occurs in between the rubidium and europium layers inside the iron arsenide planes. So certainly I will show you the evidence that those orbitals which form the superconducting pairs comes from the iron arsenide almost plane flat planes. Now, this picture shows the top view of how it appears in scanning tunneling microscope. It's actually morphology of the surface, of the cleaved surface. So we go along this dashed line and see flat steps which can be identified due to the difference in height. So we see that mainly the step size is 1.3 nanometers, which correspond to the total height of this double stack structure. But rarely, still, it happens that there are steps of the halved height, 0.6 nanometers. So we conclude from this and from other experiments that the mainly crystal cleaves along the rubidium planes, and rarely along the europium planes. It's natural because their atomic radius of the rubidium is considerably larger than that of the europium. So it's clear that to study under this under these cleaved planes, it's hard to study the superconducting properties, which must be located at least 0.6 nanometers away. And also the magnetic properties are not easy to study locally because they are also 0.6 nanometers away. Therefore, the results require some interpretation. To remind you the appearance of superconducting pairing, I show the old picture suggested by Igor Mazin and by other people like Korshunov. So basically, in all these materials of the 122 class of iron arsenide, there are two electron and hole bands which form several, for simplicity, cylinders along the gamma point and along the X or M points of the Brillouin zone. So they are elongated along the plane perpendicular to the screen, and there are some vector which almost tend to is responsible for fluctuations and provides the pairing. This is the picture behind the magnetic fluctuations, and if one take measurements of the spectrum of excitation, there should be a peak, and this peak also was found in neutron measurements, neutron scattering. So most of theorists and experimentalists currently consider that this picture is behind the magnetic pairing. So pairing happened due to magnetic fluctuations in the two-band electronic system of iron arsenide orbitals. Now, first of all, we have to take a look at the band structure. It's indeed, as it follows from ARPES measurements, it consists of several cylinders which are directed perpendicular to the screen, and some of them, at some points, like this point of the Brillouin zone, we can identify 3 cylinders. At other points, 2 almost coincide, so we see 2 cylinders only. And there are some figures, which at certain planes in the Brillouin zone can look like cylinders, but actually they sometimes look like as a propeller. So some deformed cylinders. Anyhow, this picture is almost consistent with theoretically calculated this band structure DFT calculations. And there is nothing special, it's already well established. I don't see here any puzzles. So experiment reveals nicely the valence band belonging to these cylinders and the electron bands, which are located at the endpoints of the center, at the endpoints of the Brillouin zone, and extends up. Again, this picture shows where these results can be identified with gamma points, and previous results can be identified with the endpoint of the Brillouin zone. So everything is clear here and understood, and I don't see any puzzles. So far, so good. And this is done in ARPES machine. Now we have to take a look at the calculations of the band structure, and we identify all these pieces of the Fermi surface with the electron bands and the hole bands. The hole bands are located in the center of the Brillouin zone, slightly deformed cylinders, and the electron bands are in the vicinity of the endpoint. So basically we conclude that the experiment and calculations are mainly in agreement with each other, without minor details which are not very much important, and in total picture is similar to that specific for 122 materials. And so far at this level, at the Fermi level, I don't see any difference, any major difference with 122 materials. Now we shift gears to superconducting properties of this compound. And first of all, as we do ARPES measurements, we can trace also the evolution of the superconducting gap. So we can do it because these are momentum selective measurements. We take measurements in as a function of energy, tracing different position of say valence band and electron bands, and we see how the the energy states as a function of temperature transforms, and the spectral weight transfers to the wings, so just clearly showing development of the superconducting gap. This is in more details, shows the movie of development of the gap as you go from above superconducting temperature, say 40 Kelvin, to the superconducting state. And this picture, this movie, again inconsistent with some diagrams which are here. So for those people like Ernst Hirsch who require precisely the raw experimental data from experimentalists, I show you here the raw experimental data, they come out from the machine. So one can see here not only the movie, but really the real data, how the spectra are changed, how they evolve as we cool the system down at various orientations of the momentum and various points of the brilliant zone. So indeed there is a clear indication of the superconducting gap development in the material. Now, since these are momentum resolved measurements, we identify with no discussion which gap belongs to what Fermi surface sheets. In these measurements, we identified three gaps. The largest gap actually belongs to the two pockets. One of them is a hole and another one is an electron, and the error bars are insufficient to resolve the two of them. So they evolve versus temperature in a rather usual fashion. There is nothing specific, like a BCS. And what we can conclude that this superconducting picture indeed confirmed the four-band superconducting state in this material. And there is a large band. Mainly this superconducting condensate comes from the cylinders, from the whole band cylinders. So we do the same for electron pockets and nothing special. Basically, this picture confirms what can be found in 122 materials. So these are results in a larger scale. The important question is what happens in the vicinity of the magnetic transition, because we were motivated in these studies even to see any deviation in the vicinity of the magnetic transition, to answer the question how the magnetic ordering affects the superconducting parent. We do not see with this resolution, we do not see any impact of the magnetic ordering on the superconducting states. And we have to apply another instruments to see the potential coupling between magnetism and superconductivity. So we do superconducting, we do the scanning tunneling spectroscopy. Since the cleaved sample, since the sample cleaved under high vacuum at low temperatures exposes the rubidium surface, which is 0.6 nanometers away of the superconducting plate, it is hard to see, hard to expect even to anticipate the true superconducting gap. So we can reveal with a high, after hard work, we can reveal a tiny signature of the superconducting gap, which is here may be seen as a 20% drop in the vicinity of the zero bias voltage. But nevertheless, the scale, the energy scale is consistent with what is found from ARPES. Remember, I showed 8 milli-electron volt, the large gap. So this instrument is not very helpful for us. At the moment, nothing to say additional about superconducting state, and we used another instrument which is break junction technique. Yesterday we attended 2 talks on this technique, so I don't explain what is going on. And we cleaved again the sample in the cryogenic environment, and we tuned the cleft in such a way that until we observe the Andreev type IV curve, where the zero bias conductance is twice larger than in the normal part. And in this mode, we observe several resonances which can be identified with the 2 gaps. And this picture, 3D picture, shows how this superconducting gaps evolve as a function of temperature. They clearly close at the same temperature. And this picture actually our goal. And again, with a much higher precision than from RPS measurements, we can say that there is nothing happen with the amplitude of the order parameter at the temperature where the magnetic transition occurs. So somehow at this point, we can say that the magnetism and superconductivity are decoupled from each other. And actually this the reason why we see so the Andreev reflection spectroscopy is momentum average. So after some thinking and processing, we can identify these 2 gaps as a combination of those 4 gaps which can be seen in RPS. In some measurements we saw 3 gaps, but I don't have detailed data to show the full development. Nevertheless, in total they are consistent with the RPS, but again the main conclusion is that we do not observe any deviation of the smooth behavior at the magnetic transition temperature. So we move further to the magnetic properties of this compound. When we take measurements of the low frequency or DC magnetic susceptibility, beside the standard superconducting transition at 35K, we see here a dump, which is due to magnetic ordering. So this again shows that despite we didn't observe coupling between magnetic ordering and superconductivity, still there is something happens. It can be seen here as well. And when we trace the temperature dependence of the susceptibility as a temperature dependence of the susceptibility above the magnetic transition, it follows the standard shape, the standard form, which confirms the antiferromagnetic order in total to establish in our system. Okay, now this picture of the band structure I already showed you, and I want to understand where the energy levels are located, those levels which are responsible for the magnetic ordering. So the European levels clearly. So for this we have to move to lower energy, and we indeed find a bunch of levels which are located at about minus 1.8 electron volts below the Fermi energy. So here are the levels responsible for the superconductivity, and these are clearly for magnetic ordering. Since this is the result of calculations, so they can be identified with the European F electrons, whereas those which are at the vicinity of the Fermi surface, these are Fermi 3D electrons. Now clearly another reason of the decoupling between the superconductivity and magnetism is the fact that they are located at very high energy difference from each other, so that they do not talk with each other at at low temperatures at least. Okay. The long-range ordering of the local moments requires special attention, since it's not clear at the moment, despite even several talks given at this conference. So I remind you that historically you cannot imagine homogeneous, uniform ordering, magnetic ordering of the planes, of the 2D planes, and these 2D planes are These 2D planes are identified with the European layers. So for thinking on these problems, probably the first were P.W. Anderson and Suhl, who suggested cryptoferromagnetic order, where on the microscopic scale the magnetic moments change their direction, and in such a way they resolve the problem. In 1980, Butalayevsky, Rusinov, and Coolidge suggested the helical ferromagnetic ordering, where the direction of the European moments turn from layer to layer in such a way that in total the system is anti-ferromagnetic. And this indeed happens in European 1-2 system, which is non-superconducting without doping, and becomes superconducting only in the doped state. Since this, the exact way how the moments are oriented with respect to each other in different layers is a matter of a very fine competition of several driving mechanism. Therefore, it's not necessarily happens in such a fashion where the moment change by pi. Indeed, when we take measurements of the magnetization as a function of magnetic field, we see here the nice hysteresis loop, which is intrinsic to magnetic materials, and in Z type. And inside there is a hysteresis which is due to superconductivity. This hysteresis disappears when you go to the critical temperature. Just roughly from the amplitude of the saturation, you can estimate the magnetic moment of the European, which is 6.4 Bohr magnetons, and this is roughly consistent with the textbook value of 7 Bohr magnetons. Now the calculations can be done for various type of magnetic ordering. Here the 3 examples are given. The first is a fully ferromagnetic type ordering between European planes, and the second is anti-ferromagnetic pi over 2 pi angle, and the second is pi over 2. The third is pi over 2 type, where the magnetic moments rotate perpendicular direction from plane to plane. The result, which is compared for these 3, is the ground state energy. It's almost the same but still it's slightly lower for the AFM 90, so that preferable directions of rotation angle between the planes, European planes, is 90 degrees. According to this DFT calculation, but as you well know, the DFT calculation is have a quite a large uncertainty. Nevertheless, we focus on these European levels and want to understand what type of precisely the magnetic order happens in this inside this layer. Even such a macroscopic or such a distant probe like superconducting tunneling spectroscopy reveal that at the bias voltage of about 2 volts there is a sharp feature which can be identified as due to the European 4F states. And this is again maybe seen here in ARPIS measurements, where the bunch of European levels are located at the distance minus 1.6 or 7 below the Fermi energy. More information can be obtained from resonance photoelectron spectroscopy measurements at high energy of photons, which here the picture shows the response in intensity at about 142 electron volts, which is due to the resonant transition in European 4F6 to 4F7 threshold. And it shows the multiplet of states which are, and the spectral weight transfers from the side levels to the ground state as we cool down the temperature. The first, what is seen here, that nothing happens at superconducting temperature. So again, the superconductivity onset doesn't affect on the magnetic state of Europe. Second, these measurements indeed confirm that the European is in expected state, and the magnetic moment is 704 in Bohr magnetons, and it is nicely consistent with the calculated 697 Bohr magnetons. But the picture shows that indeed, as you go to the magnetic ordering state, magnetically ordered state, the spectral weight here transfers to the ground state, and the lower states of Europium are almost out of game and do not affect anything here. Now, we may summarize the result as follows. Clearly, the Fermi surface of this compound consists of multiple hole-like and electron-like sheets, and this is similar to 1-2 system, which is well known. The superconducting gap, which is probed by tree technique, by ARPIS, by Andreev spectroscopy, and by by scanning tunneling microscope, doesn't show any nodes, so we conclude that this is a nodeless superconducting gap, and its temperature dependence is consistent with BCS, so we didn't observe any anomalies. Superconducting gaps doesn't show any features at the temperature of magnetic ordering of the European spins, and it would be, however, too premature to conclude that superconductivity and magnetism is decoupled fully. What we know for sure that Europium 4F states are located far away of the Fermi level, and therefore it is reasonable to expect that the itinerant electrons and localized moments do not interact in strongly, at least in a simple way. Other experiments and calculations suggest that the Europium states order alternate in a helical structure, and possibly with a structure where the direction of magnetization rotates by 90 degrees from one plane to another plane. And so there's two factors that electron layer, that superconducting layer and layer of europiums is 1.3 nanometers away, too far away of each other. And the second fact is that in energy they are located by 1.8 electron volts away of each other. So these two facts might show that this is a very trivial answer of the decoupling of superconductivity and magnetism from each other. But I don't think that this is the end of the story, because the impact of the magnetic ordering was found on the superconductite density rather than on the amplitude of the order parameter. So far, this is the only experimental data, and this for sure should be verified by using different techniques. We have a preliminary data that also show this to happen in the system, but I don't have them ready to show. Another contribution to this story comes from resonant Bragg neutron diffraction from low energy elastic Bragg diffractions and from resonant gamma scattering. These measurements, I show only here the results for resonant gamma scattering. They identify I showed here the data from Bragg low energy neutral diffraction. They identified beyond the anticipated periodicity related to the crystal structure. They identify the additional peak, which actually located at 1.25 of the 0.25 of the period of the latest period, and this peak, additional peak structure, disappears at the magnetic ordering temperature, and this is accepted now as a clear evidence for the 90 degrees orientation between the 19 degrees helix in the European planes. There are how it happens shown here schematically on this picture. Your magnetic moment rotates from one plane to another plane. It is also confirmed by calculations. However, the calculations are not rather are not the calculation starts from this point taken in experiment and explain why it might occur rather than they deduce it from the first principles. So it would be, of course, very desirable to have first principle calculation to deduce the type of ordering. If we think about the mechanism that might be responsible for torquing between each other the European levels. Certainly, the European levels, European planes which are located far away of each other, they somehow should interact. And it's not evident how it happens because the distance is too large. It's 1.3 nanometers for the direct exchange to happen. Therefore, it is suggested that the interaction between the European planes occurs via itinerant electrons. Evidently, it's easy to say, but it's hard to understand how one and the same electrons participate in the, which are iron electrons, how they participate in superconducting pairing, and at the same time transfer the magnetization. If this to happen, they should be reflected in the drop in the density of condensate, not by a tiny amount, but a significant amount, which is not noticed. If it happens via tunneling of other orbitals, that should be identified. And so far, this question, I would say that this question is not clear completely. I said already that this experiment should be verified and with different other type of measurements. There are some speculations about new Majorana platform for these materials, which combines in one and the same compound the magnetism and superconductivity. So one may speculate about the Majorana physics in this material to happen. And the last issue I already said about the very intrinsic mechanism behind the transfer of European magnetization between the planes, how it occurs via electrons, and actually which electrons not clear completely. So they certainly should be explored. And at this point I would like to stop and thank you for attention.
Yeah. Yes. So according to this data, the largest gap develops on the largest hole barrel. Is it right?
The large gap belongs to the electron pocket at the M point, and as far as I remember, the inner cylinder at the inner cylinder. And the smaller gap belongs to the two other cylinders. So actually, the order is the same as in 1, 2, 2 material.